Yes. Good morning. Our first chapter is real numbers. Is it?
Yes, yes, ma'am.
Last year we have learned rational numbers and we have an idea about the irrational numbers also. Okay, we know that root 2, root 3 all are irrational numbers. And in 8th standard, we have learned the rational numbers. Rational numbers means all the whole numbers, integers and fraction, and even fraction with negative numbers. All these are including in rational numbers. Then while coming to irrational numbers, they are root 2, root 3, which cannot be expressed as these terminating decimals. Suppose the decimal expansions are non-terminating and non-repeating, they are irrational numbers. You all are having an idea. Now this year we are going to learn about real numbers. Real numbers means the set of numbers which include all the set numbers whichever learned till now. Suppose whole numbers, integers, rational numbers, irrational numbers, all these are including in real numbers. So in this chapter, not only specially as real numbers will include all the set of numbers. So we are going to learn some properties of all the numbers, maybe integers, whole numbers, some special properties, whichever we have not learned till now. Okay, or otherwise we have learned still with some other names, with theoretical names, we are going to learn all that. In that, the first is Euclid's division lemma, and second is fundamental theorem of arithmetic. The main two things are in this topics are in this chapter, and after that again we will revise that irrational numbers and rational numbers, there's some special properties. Okay, let us see now. First, Euclid's division lemma. Last year we have learned here the name Euclid for that Euclid geometry, but this is different. Euclid's division lemma is for arithmetic and this is for the numbers. Let us see now. The first thing, Euclid's division lemma is actually the familiar thing whichever we have learned till now, but it is with this new name. Here, if it is given positive integers, two positive integers, suppose we are considering it as a, b, there exists unique integers q
ये
and
सर्दी
r
है बंद केलाय
such that
आणि
a
म्हणजे माझं
is
फक्त
equal
नाव
to
दिसतं चेहरा नाही दिसत मी बंद केलं ते
b into q plus r. Now listen again. Given two positive integers a and b, there exist unique integers. You all know that unique means there will not be such other combination for this particular numbers. Is it? So q and r such that a is equal to b into q plus r, where 0 less than or equal to r and less than b. This lemma is essentially equivalent to, suppose this is same as our long division and the relation between dividend, divisor, quotient and remainder. Okay, this division lemma is explaining same as our long division whichever we have learned from third, yeah,
Don't
fourth
do it.
standard. So dividend, divisor, quotient and remainder, that relation we all clear about that. Dividend is equal to divisor into quotient plus remainder. Okay, then the quotient and remainder for given pair of dividend and divisor. If the dividend and divisor is given, then the quotient and remainder obtained are going to be unique. There is no chances that you will get for any two positive numbers, there will be no chances that you will get different quotient and remainder. Okay, always whenever we are going for the division, revising it again, you will get the idea clearly. There will not be any other numbers as quotient and remainder for such particular two, dividend and divisor. Let us see now, because till now we have not noticed this in this way, as this is unique. We have learned only the division and the relation between them, and we were verifying that also. Let us see now. Here, suppose this is our division lemma. Look, this is our division lemma. I told you that any two positive numbers a and b are given, then we can write that in this form of a is equal to b into q plus r. Here, suppose a is divided by b, then Q will be the quotient and R will be the remainder. There will not be any chances for other Q and R for this particular numbers. And the very important thing you have to keep in mind is this R is always in between 0 and that divisor. Okay, let us see with some examples, then it will be clear for you. I know that now 50% of them may have doubt about, otherwise confused about all this. We have already learned that still it is given in with variables and all. Let us see now. Here, if 7 and 3 are we are considering as A and B, that means dividend and divisor. Now, then what is the relation? You all know that our normal division 7 divided by 3 is equal to 2 and the remainder is 1. That is the normal division. Now let us write that in division lemma form. That is 7 is equal to, that means A equal to 3 into 2. 3 2s are 6 plus 1, 7. So these both sides are equal. This is same as our relation that dividend is equal to divisor into quotient plus remainder. Is it? Here 0 less than or equal to 1 less than 3. Now let us see. Any number divided by 3. What will be the chances for remainders? Just think about that. Any number divided by 3. What are the chances for remainders there? Suppose any number, let us see now. If you are dividing 4 divided by 3, then what will be the remainder? 1. If 5 is dividing by 3, the remainder is 2. And if you divide 6 by 3, then it's a factor, so the remainder is 0. And again, if you are going to 7, 7 divided by 3, then the remainder is 1. Again, it started to repeat. That means 0, 1 and 2. Only 3 numbers which is less than or equal to 0 or less than 3. All these are the 3 possible remainders when 3 is divided, any number is divided by 3. Now let us see with here 19 and 5. Now let us consider A is equal to 19 and 5, B is equal to 5. That means our dividend is 19 and the divisor is 5. Then if 19 is dividing by 5, then what will be the quotient? 3. 3 5s are 15 and the remainder is 4. Now we are going to rewrite this in the form of lemma. It's 19 is equal to 5 into 3. Keep in mind again, A is equal to B into Q plus 4, the remainder. Okay. Here also the same. What are the possible remainders here? Here 0 to 5. That means it should be less than or equal to 0 or less than 5. Here the remainder is 4. That is also lying between 0 and 5. Check the relation here. Look, 0 less than or equal to R less than B. That means always the remainder is in between this. Now, before explaining these examples, let us see the uniqueness. I told you in that example while explaining that if 9 and 5 are the numbers, suppose 9 and 5 are considering as A and B. Is there any other chances that you can write that in this way? Just think about that. Is there any other chances that you can write that relation of 19 and 5 in division lemma form? That means I mean that suppose you change this quotient and remainder for these two numbers. Somebody will think that it will be in this way, 19 is equal to 5 into 2 plus whatever it here 9. But that is not possible because that is not the normal division. In normal division, the maximum number possible we will consider as quotient. Is it? So suppose if you are considering it in this way, 5 into 2 plus 5 2s are 10 plus 9. That is not the proper division. That division is wrong because the quotient whichever you are getting is wrong there. Okay. There is no other number for this Q and R for this case. That means for 9 and 19 and 5. 3 and 4 are unique. That means quotient and the remainder are unique for these two A and B. So now I think most of them are clear about how the division lemma is explained. Is it? So the division lemma is same as our normal division, and the relation between the quotient, this divisor, dividend, divisor, quotient and remainder. Okay. Now you just think about these two for 2 seconds. Just think about that. Did you understand this properly? Then I'm not going to explain this. Look by your own. Check this by your own. Then I'm going to explain this. Check all these relations. Is it correct? You are able to write such division lemmas for these given two numbers. Check that. Is there any doubt? Please note the slide number. Okay.
Students, you can jot down the important points wherever necessary, okay?
Okay, so you just note down these points. Even if it's necessary to note down any other means the slide before, if you need, just note down the number. I'll show you that at last. Okay. So let us continue. Here, these are the two relations given. Let us see with these numbers. Okay. Suppose 19 and 4 are the numbers we are using here. Here I have used 19 and 5. Let us see now for 19 and 4. It will be written in this way. 19 is equal to 4 into 4 plus 3. 16 plus 3, and 3 is always in between 0 and 4. Okay, so this is satisfying the conditions of division lemma, and we can write in the form of division lemma. So this is the division lemma we are used, where it is going to repeat again for any two given integers, positive numbers a and b, that can be represented as a is equal to b into q plus r, where q and r are unique for these two a and b. Clear? Let us see for 83 and 20. This I have given the example with the small numbers. Even for any numbers, any two positive numbers, it's not necessary to be the small numbers, any 4-digit number, 5-digit number, any two numbers you can represent it in this way. But that it should be clear here. The remainder should be in between. Otherwise, will satisfy this condition: 0 less than or equal to remainder less than the dividend. Is it divisor? Okay. Let us go for the. I hope everybody understood this. Is there any doubt? Please note the slide number. Now let us see the same question. If you are dividing a number with 5, then what are the possible values of remainder? Till now, most of them are clear about how it is divided and what are the possible values of remainder if one number is dividing by other. Let us see here any number if you are dividing by 5. What are the possible values of remainders? You know that always that remainder is 0 less than or equal to r less than or is equal to b. Less than b, not less than or equal to, because if you are dividing by 5, 5 cannot be a remainder. Okay, so it will be in this way. Here it will be 0, 1, 2, 3 and 4. All these 5 numbers are the possible remainders if you are dividing a number by 5. Now let us explain this again. As usual, it is here dividend is equal to divisor into quotient plus remainder, the same relation whichever we have learned, where if the divisor is a factor of dividend, then the remainder will be 0, and if the remainder is not, if the divisor is not a factor, you will get a remainder which is less than the divisor. Okay, it's following in all divisions. The same rule is followed in all the divisions. Clear for all of you? From your face expression, I want to make it clear. Okay, yeah. So always keep this in mind. The remainder will be always greater than or equal to 0 but less than the divisor. Okay. So now make this concept clear, then only we can use that for the other means for the application. Suppose we are going to use this for LCM and for calculating HCF and for the proving other properties of our integers, positive integers. Okay, let us see now. Now next is Euclid's division algorithm. I told Euclid's division lemma, and here this algorithm next. Algorithm means nothing else that series of steps involved in solving a problem. While we are solving a problem, we will write the systematic steps. That steps are known as the algorithm of that problem. Okay. So here Euclid's division algorithm is a technique of using Euclid's division lemma. We are going to use division lemma repeatedly, means not only one time, how many times it's required. According to the question, the number of steps will increase or decrease. Let us see now here. So Euclid division algorithm is the technique of using division lemma repeatedly step by step to compute the HCF of a given number. Actually, you all learned about the division method of calculating HCF. Is it? There were two methods to calculate HCF. I think you all are remembering. You all started this from 5th standard. 6th standard we have used the prime factorization method and the division method also. Okay, you already learned the division method from 5th standard. Let us see, even with example, I'll explain that here. Here, the prime factorization method I have not given. Okay, it's already clear. Many times we have done. So here we are going to use the Euclid's division lemma to find the HCF of two numbers. Check now. Find the HCF of 455 and 42. Two numbers are given, and first let us see how to write the division lemma for these two numbers. Division lemma for these two numbers is same as 455 divided by 42. We have to check how many times 42 will go in this. So here I have shown the division also. Okay, 455 divided by 42, it will go 10 times. Okay, it is divisible that 10 times. We know that 10 into 42 is equal to 420 and the remainder is 35. So check this part now. Okay, only this division. We will go for the other side now. Till here it is. Here the dividend and the divisor, quotient and the remainder. Let us see now. We are going to write that in division lemma form. 455 is equal to 42 into 10 plus 35. So the first application of division lemma we have done. Okay. Now let us see. Here the remainder is 35. Okay. For calculating HCF, we are going to repeat this division lemma till get the remainder as 0. Okay, we will repeat this till we are getting the remainder as 0. Let us see now what will be the next set of division lemma you are considering. For the next set, whatever the divisor you have used here, that will be the dividend. Okay, here let us see dividend and here divisor. Whatever the remainder, that will be considered as the divisor. Okay, then we will calculate, otherwise doing that, otherwise computing that division. Doing the division, you will get 1. The quotient is 1. 1 into 35, 35, and the remainder is 7. Now check this division. This dividend, divisor, quotient, and remainder. Okay, let us see now. 42 is equal to, you know that A is equal to B into Q plus R. Is it? Here 42 is equal to 35 into 1 plus 7. Again let us check. The remainder is not equal to 0. Okay. we are repeating the calculation again. Otherwise, we are repeating the process again. Here, again, here the divisor, that will be the dividend. Divisor is the dividend here, and whatever the remainder in the preceding step, that will be the dividend, this divisor here. And after calculating this, after doing this division, we are getting 5 as the quotient, okay, and remainder is equal to 0. So for again we are writing as division lemma form, and you are getting 35 is equal to 7 into 5 plus 0. So we are going to stop this division lemma method, otherwise process here. And after, if you are getting such a step at last, from the whatever the divisor in that step, whatever the this divisor in that last step means wherever the remainder is 0, that divisor is the HCF of these two numbers. Okay, that is the HCF of these two numbers. Repeating again, for the HCF of 455 and 42, first you have to divide that and write that in division lemma form. The division lemma form is already explained with many examples. I think most of them are clear about that. So we will write all of them, means not most, all of them are clear because we have explained with first to 6 examples here. So 455, 42 into 10 plus 35. Again, the only one thing you have to keep in mind, what is the, for the next step, what is the quotient, what is the dividend, divisor, and how to calculate the division. Is it? Then here 455, here this is the divisor, here that is the quotient, and the here that is the dividend, and this remainder is the divisor here. Okay, again this divisor is dividend here, and the remainder is divisor here. Okay, and automatically we will get the quotient and the remainder, and wherever you are getting 0 as the remainder, from there we will get the HCF of that two numbers. Okay, such questions are included in worksheet, so you are going to solve that. Okay, now it is clear. So whichever the given worksheet, such questions are included, so you have to solve that. Let us go for next now. Here, find the HCF of two numbers 250 and 75. Here the division is not given. So whenever you are using the or applying the Euclid division lemma, you will write that general form in this way. Okay, suppose A and B are any two positive integers, in this way any two numbers we are considering, you will write it in this way, the general form A equal to BQ plus R, where 0 less than or equal to R less than or equal to B. And always while before doing this, you should assume it in this way properly, then it will be easy to compute. Otherwise, do that process. Here, for this case, A is equal to 250 and B equal to 75. And one more thing, there will be a confusion, which will be A, which will be B. So always take the greater number as A and the smaller as B. So while two numbers are given, then for the both, the first greater will consider as A and the smaller number will consider as B. So here again, A is equal to B into Q plus remainder. Okay, this is very easy question. You know that in 250, how many times 75? 3 times. Is it? And you're getting it as 25 as the remainder. Okay, here you will get 3 into 75 is 2 into 75 150, and 3 into 75 you are getting 225, and 25 will be the remainder there. Okay, again that's 75 and remainder as the divisor, then 25 into 3 plus 0. Okay, as 0. For some questions, there will be in the first step itself, you will get the remainder 0. Which will be that condition? Just think about that. That condition is that the given numbers, the smaller number is a factor of the greater number. In such a case, if the smaller number is a factor of the greater one, then you know that there is a relation between factor multiple relation. If any the HCF of that numbers, the smaller one. Is it? If HCF is the smaller one, then what will be the remainder there? The remainder will be 0. Now, all of you please note down these two numbers. We are not going to note down the answer, but note down the numbers and the remainder also. Then later on you are going to solve this and you will get the answer. You should get the answer. Okay. Now, this division lemma or division algorithm is not only used to find the HCF. This HCF is just an introduction of that application. Okay, the main thing is different because for calculating HCF, other than this, so many division you can apply. Otherwise, the factorization method, prime factorization method, you can apply. This is just an application, introduction of the application of Euclid division lemma. The main thing is many practical application in finding the properties of numbers that are very important here. Let us see such a question. Then that will not be an easy and familiar one to you. Still, you can understand. Concentrate here properly. Okay, the time is going to be. Okay, I'm just explaining one question here. Let us see. Here, yeah, show that any positive odd integer is always in the form of 6q plus 1, 6q plus 3, and 6q plus 5. We know that any number dividing by 6, the remainders are 0, 1, 2, 3, 4, 5. Clear for all of you. So any positive integer can be represented in the form of this 6q plus 0, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, and 6q plus 5. Any positive number can be represented in the form of all these 6 cases. Okay, and we have to prove that any positive odd integer is always in the form of 6q plus 1, 6q plus 3, and 6q plus 5. Usually you know that any number 6 into q is an even number. Okay, 6 into q is an even number. If you are adding 1 to that, you will get an odd number. While adding 3 to that, you will get an odd number, and adding 5 to that, again you will get an odd number. Okay, so but systematically or theoretically, we have to prove that here 6q plus 0 is coming in the form of 2 into 3q. Okay, how it is? 0 is the remainder, 2 into 3q, it is 2m form. M is equal to 3q, be any positive integer. We are considering m as any positive integer. So let us consider now. First, that number is representing in the form of 6q plus 0. It's coming in the form of 2m, otherwise multiple of 2. That means this is an even integer. Okay, then the other phase of representation is 2m plus 1. Let us see 6q plus 1, again 2 into 3q plus 1. M is considered as 3q, and again multiple of 2, this is an even number, plus 1, we are getting an odd number. Okay, while coming to the case 3, here the remainder is 2. Suppose the remainder is 2. Then the number will be in this way 6q plus 2. This is the division lemma applied here. Okay, because a is any number and our divisor is 6. That means b is 6 and q and the possible remainders we are considering here. Okay, here 3q plus 1, 2 into 3q while taking 2 as the common factor. Here it is 2m. M is any positive integer we are considering in different cases. Any positive integer, so the value of m is getting changed here. For each case 3q plus 1, and it is in the form of 2 into m. This is an even integer. Okay, multiple of 2, so it is an even integer. Now coming to case 4, that means the radius remainder is. Now you can see here, if the remainder is 3, a is equal to 6q plus 3. To convert this to the familiar, otherwise the necessary form, we are going to write it as 6q plus, this 3 is written in this way, 2 plus 1, okay, which is 2q, 2 into 3q plus 1 plus 1. That means again multiple of 2, 2m plus 1, this is an odd integer. Multiple of 2 is even, plus 1 is an odd integer. Now again for the case 4, here this is an even integer, and Let us see 6 cube plus 4. For that case, the remainder is 4. 2 into 3 cube plus 2 coming as 2m. Yes, who didn't understand that? This is an even integer. And the last set I'm not explaining, just check it. Case, sixth case, suppose the remainder 5, you will represent a is equal to 6 cube plus 5. Okay? And you're getting this 6 cube plus 4 plus 1, and this is an odd integer. Yes, I'm going to explain this again. Let us check it again in this way. So let us see total 6 cases. In that 3 cases you are getting these are odd integers. Which are the cases? The 6 cube plus 5, 6 cube plus 3 and 6 cube plus 1. So here it is proved. They have given the question, show that any positive odd integer is always in the form of 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5. Yes, I'm going to stop this here now. Only 4 minutes are remaining now. Chitra ma'am, please unmute them. Then otherwise they can unmute by their own and ask their doubts now. Okay. These are the one more question is the same type, and the 2 questions are given for HCF and LCM. It's already done last year. Okay. Yeah, fundamental we will do in next class. Okay. I think in this you are having doubt. All are there? I think you can unmute by your own.
Yes, ma'am. Yes, ma'am.
Yes. Yes, this is the page we were explaining now. Okay, first of all, you all understood this, whichever explained. Only 2 things explained now. Is it the division lemma and the application of that, the algorithm? Okay.
Yes, ma'am.
Yes.
Division lemma is clear for all of you?
Yes, ma'am.
Yes, ma'am.
Clear? Okay, tell me now, what are the possible remainders if you divide a number by 7?
0 to 6.
2, 3,
0,
4, 5,
1.
6.
0, 6.
0
to 6.
Yeah, very good. 0 to 6. Very good. You all know. And you know the form how to write that. Is it?
Yes, ma'am.
Will be in the form of A equal to BQ plus R. So the last question. This is very now the division lemma. By applying the division lemma, how to do the HCF? It's clear for all of you. Is it? And the other
Yes, ma'am.
application is this one. Okay. In this, you just think about now. Number is dividing by 6, and the possible remainders are this. And we are writing all the cases. Then you will check what is to be proved. Okay, you will write all the 6 cases in this way with the possible remainders. Go through this, then you will get the idea.
Yes, ma'am.
Okay,
Yes, ma'am.
I think one worksheet is already given. The such questions are not included. I will check it again. Okay, then I'll give one more worksheet by including such questions, and you have to solve that. Okay, and we will
Yes,
arrange
ma'am.
one more session for this chapter. That time we'll explain that questions also. Is there any particular doubt for any page? Please give me the page number.
No, ma'am.
No, ma'am.
No, ma'am.
Thank you.
No,
Okay,
ma'am.
check it again. Okay, I'll send the worksheet with the examples also. Okay, then you can do it.
Yes, ma'am.
Yes, ma'am.
Sure. Thank you, ma'am.
Check the page, this page again. If it necessary, take a click. Otherwise, screen print.
Thank you, ma'am.
Take a screen print of this.
Thank you,
Then
ma'am.
it will be easy for
Thank you,
you.
ma'am.
All are present today.
Yeah, kind of.
Yes, ma'am.
Most of them.
I think
I'm
so.
going to this.